So an even number is any number that can be divided by 2 with no remainder. That's actually an important concept. Just to let you guys know what we're doing today. We're going to do a couple different things. The very first thing we're doing is really kind of helping work with your number sets. So while you may understand an even number is any number that can be divided by 2, divided evenly by 2, what that means for you is what we're going to get to. But to get to it, we need to start with some of this basic stuff. The second part is, and there's a really kind of a second part to the even number. How do I know just looking at a number that it's even? What do you think, Arthur?
Just looking at it?
Yep. Just looking at the number, how do I know that it's even? Paul?
You have a 0, 2, 4, 6, 8.
Where?
Where?
No.
Last number.
Last number. So it ends in 0, 2, 4, 6, or 8. Okay? So if I look at a number, and it doesn't matter what the number is, as long as that last digit is a 0, 2, 4, 6, or 8, I know that it is even, correct? Everybody good with that? Mm-hmm. So what are some examples of even numbers? Allie? 36, good. Give me another one.
42.
42. What about a bigger one? Michael?
164.
164. So even though it starts with an odd number, that is really irrelevant, right? It's only what it ends with. That tells us what an even number is. We'll do one more. Xavier?
1,569. Wait, no. 105,000. Wait, no. 1,560.
16?
60.
60, okay. Yes. You had me worried when you said 69.
I know. I was about to say it.
Now, conversely, what is an odd number then? Kennedy?
Any number that can't be divided by 2 with no.
Okay. We'll just say cannot be evenly divided by 2. So just as we could look at an even number and know it's even, how do I know it's an odd number? What do you think, Isaac?
It does not have 0, 2, 4, 6, or 8 at the end.
So what numbers does that leave us?
1, 2, 1, 5, 7, and 9.
There. So again, it doesn't matter what the number is. So give me some examples of some odd numbers. Did you already get one? You guys both gave one. Israel, give me an odd one. Good. Arthur?
10,000. No, yeah, 2,569.
Good.
A billion what?
Billion what?
A billion and one.
A billion and 1. Again, it doesn't matter how many numbers there are, or if my smartboard doesn't work, the number itself is still odd. Those are zeros in there. 1 billion and 1. So you guys get the idea, right? The bottom line is that just by looking at a number, I should be able to tell if it's odd or even. Why is this helpful? Because what happens if I add 2 even numbers?
It goes to the odd.
So if I add 2 evens, it becomes odd, right?
No.
2 plus 2.
2 even, is that always the case?
No.
So there's never a case where I can add 2 even numbers to get an odd answer? Bottom line, yes, it will always be even. So if we turn the page, we're going to take a moment and we're going to talk about some examples of this. So go to your next page. So why is the sum of 2 numbers even? we're going to do some representation, some modeling to help you understand why this actually works. So we're going to model 12 and 14, and to do so, we're just going to do dot patterns. And we're going to do them in pairs. So we'll do 12 dots done in pairs, so 6 rows of 2. And then we're going to add 14, so that's going to be 7 rows of 2. The next step on this is we're actually going to now circle all of the dots that are in pairs. So for each pair of dots, we're just going to be one big circle. With our 2 numbers now, you should see a pattern.
Some of them are self-dotting. Some of them are drawing circles and shading it, so it's taking them a bit of time.
They don't have to be perfect, guys. So is this going to be true every time I add 2 even numbers? Will I ever be able to do an even number where I don't have complete sets of dots? No, not on either side of that, correct? So why is it that it will always be even? Good, because every dot will have a partner.
Nobody's left out.
No one's left out. Not yet, anyway. On the evens, nobody's left out.
I forgot we're being recorded.
So every dot will have a partner if it's even. So regardless of the numbers I'm going to use, because they're all set up as evens, when I add 2 even numbers, my answer will always be even. Now let's look at the next one. What about 2 odd numbers? Why is the sum of 2 odd numbers always even? And start with 2 odd numbers, why is my answer even? So let's look at another problem. We're going to do 11 and 15. So just as we did, let's draw dots to represent it. So 11 dots. And then we're going to add 15 dots. Now, just as we did in the last set, we're going to circle our pairs of dots. So our first one, the 11, we have 5 pairs, but then we've got that one guy that's left by himself, right?
Yeah.
On our second one, we have 7 pairs, but it also has one guy left out. So if I'm going to circle pairs, guess what I can do? I can put those 2 single ones together. That is now an additional pair, isn't it?
Yeah.
Will this ever change despite the size of the odd number? No. So why is it that every time I add 2 odd numbers, the answer is even? Allie?
Because you can always bring the one that's left over onto the other side to make another pair.
Does that make sense?
Yeah.
Yes. So, because each odd number will have one left over, to form an additional pair. So this is why if I add 2 even numbers, I get or 2 odd numbers, I get an even result. Everybody tracking so far? Good. Let's look at our next one. What's that? You're actually writing? Man, I'm impressed. Maybe we should record more often for these guys. We are. That's where we circle. B just says circle the pairs. Okay, next page. Now we're going to look at an even and an odd and understand now why my answer will be odd. This is the third page. Are you going front to back, Michael? Okay, so we're going to do 14 and 11. So just as we've been doing, we're going to do 14 dots, so 7 sets of 2. And we're going to add 11. Just as we've been doing, we're going to go ahead and circle our pairs. So our 14 is going to give us 7 pairs of dots. On the 11, we're going to end up with 5 pairs of dots. And 1 is left over. So once again, does it matter how large the number is? No. As long as it's even or odd is what matters, because the evens will always be made up of sets of dots. But the odd is always going to have that 1 left over, correct? So, why is it always going to be an odd result, Jocelyn?
Because it's another dot to form an additional pair.
Good. There will always be 1 dot left alone. That poor little dot has no partner in this world. It is kind of sad. It's like certain students we have in here, but we won't mention names. Now, here's a quick question. What if I did the first number, instead of my first number being even, what if I switched it and made this the odd and that the even? Doesn't matter. Why not?
Because you're just what you can get around. It's like multiplication and addition, multiplication, it doesn't matter if it's switched around.
What property is that?
Commutative
property.
Yes. Thank you for finishing it. Commutative property of addition. Basically, all that says is it doesn't matter what order I do the operation in with addition, I'm going to get the same result. So 11 plus 14 is the same as 14 plus 11. But it is actually really important, guys, that we add that of addition. We do not have a commutative property of subtraction, do we? No. So let's sum up what we just learned in our little experiment here. If I take an even and add an even number to it, my result is even. If I take an odd number and add an odd number to it, my result is even. If I take an even number and add an odd number, the result is odd. Okay? But guys, I'll be honest, first time I looked at this lesson, I was like, I don't know if I want to teach this. But I actually think that's a really important concept for you to understand. Because when you're doing tests, this is a really simple way for you to say, did I make a simple math error? If I'm adding 2 even numbers, I get an odd result, go back and check it. That is super quick and easy to check. But now you also understand why. Now let's look at product. So now I'm going to do product of 2 even numbers, meaning I'm going to multiply. So they didn't give us examples. Let's just make one up. I don't want to do a whole ton of dots. So let's go, for example, 2 times 4. Now, because we're going to model, is that going to look any different than 4 times 2?
No.
Wrong. It will look different. What is the difference? If I say 2 times 4, what does my model look like? Olivia? Good. what this is saying is it's 2 groups of 4. So remember that multiplication is actually just repeated addition, right? So this is actually the same way as saying this. 4 plus 4. So just as we did last time, if I do this and I circle my pairs, what do I find?
8.
If I multiply 2 even numbers, what is my result going to be? Even. So the product of 2 even numbers is even. That is a true statement.
Do y'all see the difference between 2 groups of 4 and 4 groups of 2?
Because our 4 groups of 2 would look like this for a model. It would be 4 or 2 plus 2 plus 2 plus 2 plus 2.
Do you get the same answer?
That'd be 5. Yeah, that's 5.
2, 3. I did do 5. I got so concerned with my erasing, not showing up writing, I got carried away. So the models do look a little different. Result is the same. What property says that? You guys are close, but you're not right yet. There you go. Commutative property of multiplication. Commutative property of multiplication. Says my result is going to be the same regardless of which way I do the math on those, but the model does look different. So be aware of what those numbers mean, because as we get later on, the order does matter. What about the product of 2 odd numbers is odd? Is that going to be true or false? False, right? Okay, so let's look at a model and see. So again, I don't want to do a ton of dots. Let's do 3 times 5. So I have 3 times 5. We're going to have groups of 5. So there's 1 group, 2 groups.
3 times 5. That's 5 times.
That is 3 groups of 5.
Oh, wait.
You're correct in that that would look different than 5 times 3. That would be 5 groups of 3. Miss T?
Write the words that might help you get 3 groups of 5.
Again, the result would be the same because of the commutative property of multiplication. However, the model does look slightly different. 3, 4, there's 5. So doing our same task, let's put together our pairs. We have a pair here with a loner, pair here with a loner, pair here with a loner. So I have 2 of those loners that can make an additional pair. But what do we see? We got one lone guy left out there, right? What if we did the 5 groups of 3? Well, those are a little different. Now I've got a set there. I've got a set there. Oh, then I've still got a loner. So if I multiply 2 odds, will my answer be odd?
Yes.
Yes, so that is not false. This is also true. So now our last one, the product of an even number and an odd number is even. Is that one true or false?
True. No, false.
I heard you say true first.
Is it true? I think it's true.
Arthur's going with true, right, Arthur?
I go with false. It's true. False.
Let's take a look.
15 times 3.
Okay, let's try one. Okay, even and odd, let's do 2 times 5.
4 times 3.
Even and odd. So we're going to do 2 groups of 5. So I've got 5 here and an additional 5. Using our dots, we can put together our pairs. Oh, there's a loner, another pair and a loner, and what do we see? additional pair. So, is the product of an even number and an odd number even?
Yes.
Yes. Arthur was right before he changed his mind. That was actually true.
Did I change my mind again?
You did. You guys understand why that is? Okay, that was the whole purpose of this entire exercise, guys. Now, keynote here. Without solving, this is your homework. So, do I want to see a whole bunch of work done over here? No, I don't want to see any. All I want you to do, guys, is put these into effect. The sum of two even numbers is even.
Oh, that's good.
The sum of two odd numbers is even. The sum of an even and odd number is odd. Here's where it changes. Product of two even numbers, even. That's the same. That's the one thing that's the same between adding and multiplying. But with multiplying, the product of two odd numbers is odd. That's a switch. With multiplying, product of an even and odd is even. That's a switch. So the only rule that remains the same between adding and multiplying is two evens is always even. Other than that, you have to understand what the rules are and why, which is why we went through that whole process of doing the dots to show you why. You guys feel okay on that? So explain your reasoning. That should be very simple. They gave you the reasons right above, guys.
Wait,
Yes.
so we just have to put like true or false?
No, you have to put even or odd.
Oh.
And then you have to explain why.
Okay.
And the explanation is literally right there above.
I'm still gonna ask my dad.
Okay, I need you guys to do something for me real quick. I want you to write beside greatest common factor, write least common multiple.
We've moved on, guys. Let's go. Next stage.
I'm going to do my best to make this very easy for you today. Above those as well, I want you to write GCF and LCM. In math, very rarely are you actually going to see these written out. You're going to see the abbreviations GCF or LCM. What they stand for are greatest common factor and least common multiple. So if I give you two numbers like 12 and 18, which is going to give me the larger result? The greatest common factor or the least common multiple? Which number will be bigger? Greatest common factor, right? Makes sense, right? So this one is going to be the bigger of the two. Don't write that yet. Why would you say that, Paul? Because it says greatest. That makes sense, doesn't it? That's why this doesn't make sense, because you're looking at the wrong piece. What if I look at factors versus multiples? Multiples are bigger.
What's a factor? Christina, what's a factor?
So 8 is a factor to get to the answer of the multiplication problem.
Okay, so then what's a multiple? What's a multiple of 10?
20.
Oh, okay. So did y'all hear that on that side of the room? So what's a factor? So what are some factors of 24? 6 and 4. What else? 12 and 2. 24 and 1. Those are factors of 24. So what are some multiples of 24? 24, 48. That's probably about as high as we can go in our head. So do we see the difference between a factor and a multiple?
72.
Thank you for the delayed response.
So the bottom line, guys, is the least common multiple of two numbers is actually going to be bigger than the greatest common factor of two multiples. Make sure you're focusing in on the correct part of the expression, the factor versus multiple. We're going to go through 3 different ways to find GCF and LCM. 2 of them I'm just going to hit really briefly because I don't like them very much. The third one is where I really want to focus our efforts today, but I want to make sure you're exposed to all 3. The first one method is what you have done when you were first taught this back in about 4th grade, is the first time you should have seen this. And that is I list all of the factors for the numbers that I'm looking at. So for the number 12, what are all of the factors of 12?
6, 2.
Okay, I'll be honest, I always start with 1. So 1, 12, then what?
1, 2, 6.
2, 6, what else?
3, 4.
3, 4. What about for 18? What are the factors? 1, 18, because I always start at 1. 2, 9. 3, 6. Once I have listed all the factors of both numbers, what I can do is I can go through and I say, what is the biggest number that I see in both? So do I see a 12 in this one? No. Do I see a 6? Yes. So that's the biggest factor that they have in common. That is your greatest common factor. So of all the factors that each of the numbers have, that is the largest one. Okay? Now, this works okay for small numbers like 12 and 18, but once we start getting up to 144 and 196, do you really want to list all of the factors? Because here's part of the problem, guys. If you miss one set of factors, you could miss the one that is the greatest common. So that's why I don't like this. It works okay for really little numbers, but there's a lot more efficient ways to do it. One of them is what we call factor trees. So what I do is I start at my big number, 12, and I'm going to break it into its factors. And I'm going to keep breaking it down till I get all prime factors. How do I know it's prime? That's where our 4 key numbers come in, guys. So anytime we're doing GCF or LCM, the first thing you may want to do is write those 4 key numbers at the top of your paper. 2, 3, 5, and 7, because those are the ones that you're always going to come back to. So if I'm looking at 12, what can I break it down into? Well, we just listed a bunch of them here, didn't we? So I'm going to go ahead and use the first one, which is 2 and 6. As a side note, you don't ever want to use the one that's only going to be for prime numbers. If 2, 3, 5, and 7 don't go in, that means that your number is prime. On my branches, whenever I get to a prime number, I circle it. That tells me that branch is dead. I'm not going any further on it. But 6, I check my 4 key numbers. I say, oh, I can still divide that by 2. So I break it down further. That's now a 2 and a 3. Now I've got all of the branches finished. Now I can rewrite this as its prime factors, which would be 2 squared, or 2 2's, times 3. Then we go through that exact same process with 18.
Wow.
So we're going to do, I'm going to start with the same one, 2 and 9. So 2 is done. 9 is going to break down further to 3 and 3, which are both prime numbers. So for 18, our prime factorization is 2 times 3 to the second power. No, that's 3 times 3. So I apologize for the smartboard glitches here. Realize those are both 3's and those are both circled. Here's the only reason I don't like this form, guys, is this next part. Because the rules for what I use for greatest common factor and least common multiple are different. For greatest common factor, what I have to do is pull out the smallest number that they both have. So in other words, both of these have at least 1, 2, so that would be a common factor. Both of them have at least 1, 3, so that would be a common factor. When I do 2 times 3, I get 6, so my GCF equals 6. I know, it gets confusing, right? So, let me make this far easier for you. The easy way to do this is what we call the cake method. The reason it's called the cake method is because of how it builds. All I'm going to do is I'm going to start with the 2 numbers that I'm trying to find the greatest common factor and the least common multiple of. I write them down side by side, and I put a division bar over them.
Hey, if y'all are run out of space, on the back of the previous page is blank. So on the back of page 78, like literally in your packet, the back of the page to the left is blank. So if you run out of space, write this there because this is really important, okay? It's called the cake method, right? Cake method, all right? This is the easiest way to do both. So again, if you don't have space, and this is going to take up a little bit of space, please write it on the back side of that previous page.
The cake? I thought you said cake.
Nope, cake method. because you'll see in a minute it goes up like a cake. Yes, Allie.
Fourth grade, whenever we first learned this, my teacher, she taught us how to do this on our phone.
Again, for small numbers, that's okay. The problem is, you're going to see some of the examples in today, the numbers get so big that it's not going to work. So trust me on this, this is by far the easiest way to do this. In the cake method, all you're going to do is you're going to focus on those 4 key numbers, 2, 3, 5, and 7. So I'm going to look at both 12 and 18. I say, can I divide them both by 2?
Yes.
If I say yes, I write the 2 to the side just like it's a division problem. And then on the top, I'm going to write what the remainder is. So 12 divided by 2 is 6.
Maybe go to a new spot.
That's what I'm thinking. You know what? I'm just going to come down here and change my ink color. So I'm going to restart this down here. Great. So, actually over here tends to be better.
I can't
It may have just completely glitched us. Okay, so the smartboard crashed, so here's blank space. I'm just going to use this. You guys are probably on another page, but we're working through the cake method. What I'm going to do is I'm going to take my 2 numbers, 12 and 18, write them side by side, put the division bar over them. The first number I saw was 2. On the top bar goes your remainder, so it's 6 and 9.
Yay.
Okay? Here's a really important piece on the cake, guys. Every time I do a new layer, you must recheck your 4 key numbers. So can I divide 6 and 9 by 2?
No.
No, by 3?
Yes.
Yes.
And literally, you should run through it this fast. You go 2, 3, 5, 7. It shouldn't take you much time to think of any of those. So if I say yes, I put an additional number on the left-hand side, and I put the new remainders on top, 2 and 3. Well, those happen to be 2 of my four key numbers, so I know I'm done. Here's why I love the cake method the most, because we have now laid it out for you to find both the GCF and the LCM. For the GCF, you multiply the numbers on the side. So what do I mean by that? GCF is kind of like this big arrow. If I turn GCF into an arrow going straight up, I'm going to multiply 3 times 2. 3 times 2 equals what? 6. For my LCM, least common multiple, multiply all numbers on the outside. So everything on the outside now gets multiplied. So LCM is kind of like this big LCM. I'm multiplying everything on the outside. So I'm going 2 times 3, which is 6 times 2. 12 times 3 is 36. So in one quick step, I have now found both the GCF and the LCM. Make sense? So again, for greatest common factor, I'm multiplying the factors on the side. For least common multiple, I'm multiplying everything on the outside. So now that I've introduced it to you, let's look at this a couple more times and give you guys some additional practice on it. Here's the old way we used to do it. You guys can just cross that out. We're not doing this. It takes way too long. Backside. So we're instead going to write our 2 numbers. We just did that one, right?
Yeah.
Good. So we're going to go down here. So station 1, I want you to write in, we're going to do GCF and LCM of all these numbers. Because quite frankly, the only additional work to it is multiplying all the numbers. But we're going to set them up exactly the same. So our first set, we're going to do 30 and 50. So I write 30 and 50, and I write my division bar over them. One thing when you're doing the cake method, guys, make sure you leave room on the top of it, because these are going to build up while you're multiplying. So don't write it right next to the writing, because then it gets really hard to do. Here's another thing I really love about the cake method, guys. If I see a bigger number that's a common factor, I can take it. So I don't have to focus on just 2, 3, 5, and 7. If I see something really easy that is bigger that's easier, I can do that. So if I see a number that's in 30 and 50, what can I divide both those by? 10. Hopefully all of you see that right away. So 10 gives me a 3 and a 5. For my GCF, I'm just multiplying up the side. In this case, it's only one number, right? What is it? 10. For LCM, I'm multiplying everything on the outside. That's our big M. So again, because we have commutative property of multiplication, I can do it in any order I want to. I'm going to make it easy and do 5 times 3 is, times 10 is 150. So literally in just that small amount of time, guys, we just did both the GCF and the LCM. Pretty easy, right?
Yeah.
Now, quick side note, 30/50, for those of you that really want to focus on your 4 key numbers, 2, 3, 5, and 7, just to show you how that works, all we would do is I said, okay, I see both those. Can I divide them both by 2? Yes, so I do. It gives me a 15 and a 25. Then I check again. Can I divide both those by 2? Nope. By 3? No. By 5? Yes. So I do a 5. Gives me a 3 and a 5. Guess what, guys? We just did the exact same thing. I multiply those 2 for the factor. 2 times 5 gives me 10. 15 times 10 gives me 150. Same answer. Took you one extra step, but was that really hard to do? No. So 2, 3, 5, and 7 will get you to the answer. If I see something bigger, you can take that step using this method. Let's do one more together. We'll do 30 and 45. So 30, 45. Can I divide those both by 2? Or what number do you see that goes into both those easy? 5. So let's do 5. 5 gives me a 6 and a 9. What will go into 6 and 9? 3. Kayla, are you writing stuff down? This is going to get really confusing when you have absolutely nothing to work off. You could have.
Why don't you do it and see if you get the same answer?
So for the factor, I'm going to multiply up the side. 3 times 5. So my GCF is 15.
Looky there.
My LCM, I can actually do, again, the order I want. I see 5 times 2 is 10. 3 times 3 is 9. 9 times 10 gives me 90. Pretty easy, right? Okay, so I'm going to give you guys 6 minutes. I want you to finish those last 3 as a table. You can work together, but take some time, work on this, see how well you understand it. Okay, guys, if you look at these, back up front, please. Our first set, 45 and 60. GCF was 15, came out in both of them. LCM, 180. For 42 and 70, our GCF was actually 14. LCM was 210. Now, when I multiplied this one, I did 2 times 5 was 10, 3 times 7, 21. 21 times 10 made it easy. Our last one was a little more difficult. I personally saw the 12 right away. Most of you probably started a little lower. That's fine. As long as you didn't make a math error, you should have got to the same thing. Again, factor, I multiply on the side.
Oh, yeah.
So that was 4 times 12 for the factor. Was 48. My LCM is everything on the outside. When you multiply all those, you got 288. Questions? Okay, let's go ahead and turn to our next page.
What page is
So it's the one with the word problems. Okay, our first one, we've got 18 girls, 24 boys who want to participate in a trivia challenge. Each team must have the same ratio of girls and boys. What is the greatest number of teams, so there's one question, that can enter? And then find how many boys and girls each team would have. So there's actually 2 questions that we need to answer off of this. Now, one way to think about these types of word problems, guys, is just start right off with the thought. Am I going to have a smaller number or a bigger number? Smaller. So is that going to be greatest common factor or least common multiple? Greatest common factor, because that's the smaller of the two, correct? So if I look at my two numbers, 18 and 24, I'm going to try to find the greatest common factor.
6.
So I'm glad you saw 6. I would have seen it too, but just to show everybody else, if I start at my 2, 3, 5, 7, 2 would give me 9 and 12. Then I can do those two by 3, gets me 3 and 4. For my greatest common factor, again, I'm multiplying on the side. My GCF is 6. So I can make 6 teams. Here's kind of another interesting piece on this. How many boys and girls would each team have? Well, that's actually my top row. So each team would have 3 girls, because that was listed first. And 4 boys.
What about the LCM?
We don't need the LCM for this question. There are other questions later where you'll need LCM. This is not one of those. But that's why I said up front, you need to think about, am I looking at a bigger number or a smaller number? That's going to tell you, am I looking for GCF or LCM? Okay? Our second one, the ski club is preparing identical welcome kits for new skiers. They have 60 hand warmer packets and 48 foot warmer packets. Find the greatest number of identical kits that you can prepare. There's one question, using all of the hand warmer and foot warmer packets. How many hand warmer packets and foot warmer packets would each welcome kit have? So there's a second question. How many of each of those packets would each one have? So again, am I going to be looking for a bigger number or a smaller number?
Bigger.
So I'm going to get more kits than I have pieces?
Smaller.
Smaller, right? So I'm going to have a smaller number, so that means I'm finding my GCF. So I have 48 and 60.
What?
So I know both those can be divided by 2. It's going to get me 24 and 30. Well, I'm going to both 24 and 30. I'm going to do 2 again, right? Gives me 12 and 15. What will go into 12 and 15? 3. That gets me 4 and 5. Those are 2 of my key numbers, so I know I'm done. So again, for our greatest common factor, I'm going to multiply all of these on the side. 2 times 2 is 4, times 3 is 12. So I have a GCF of 12, meaning I can make 12 kits. My top line is going to show me how much of each I'm going to have. Each will have 4 foot warmers, and 5 hand warmers.
What about body warmers?
That's for the snowsuit you're wearing. Okay, I'm going to let you guys do the next one. First off, determine, are you finding GCF or LCM? Then do the work and see what your answer is. Okay, guys, let's look at this one real quickly. On our problem. Guys, come on now. We have 435 representatives, 100 senators. We're going to do identical groups with the same number of reps and senators from all, and we want the largest group possible. How many reps and senators would be on each? So we've got 2 questions again. I want how many groups can I get, and how many senators and representatives are in each. I saw a lot of people automatically struggling when you saw the bigger numbers. This is why I like the Kate, guys, because if I was trying to list all the factors, oh my gosh, what a nightmare. I wouldn't even want to start on that. If I was doing a factor tree, that's better, but then it's pulling out what I need for greatest common factor versus least common multiple is different. This makes it super easy. Literally, all I do is I go, can I divide them both by 2? No, I can't divide 435 by 2. Can I divide them both by 3? No, by 5.
Yes.
Yes. So then I do the 5. That's going to go 87 times. That's going to go 20. Then I check again. Can I divide them both by 2?
No.
By 3?
No.
By 5?
No.
By 7?
No.
If I say 4 no times, I'm done, guys.
Yeah.
That's it. How many groups can I make? 5 groups. I can make 5 groups. How many will be in each? 87 reps.
And 100
20 senators. Senators in each group. That's literally all you got to do, guys. Pretty simple, right? Okay, so here's some good news for you. Cross out D and E. Turn the page. Everybody, please look at me really quickly. Eyes up front. Israel. Israel, I need your eyes. Gavin. Presley, look. Seriously, I want everybody looking at me. Isaac. Rosalind. Eyes. You need to write what I am about to write on your homework. Because if you come back in 2 days and all you have is the LCM, you are getting half credit for your homework. Does everybody understand me?
Yes.
Yes. So what you need to write, multiples and LCM and GCF. I want both LCM and GCF for each of these problems. You can go ahead and number your problems. That's number 1, number 2, number 3, number 4, number 5, and number 6.
If it were me underneath LCM, I would go ahead and write GCF so I don't even miss it.
She's saying just go ahead and write it right there like that, guys. And you've got a couple minutes, so you have time to do that. So you want to find the LCM and GCF for each of those 5 sets of numbers, and we're only going to make you do one of the word problems. You guys can cross off B and C. Now for A2, we actually had 3 additional pages, but when we didn't get to them, we decided to cut that out for everybody. So that's why theirs is going to look a little different. But everybody else, all we had you take out was through 88, which is this page. So this is your homework. You have those 5 problems and the one on the bottom. You guys actually have 5 minutes left.